There's a nice infinite series proposed by Ramanujan to the Indian Mathematical Society back in the day. And the solution development is pretty simple and elegant as well. So let's just get started. We're going to call the sum we have S here for reference purposes, and the first thing I want to do is factor out a 4n from the denominator. So I have the sum over the positive integers n of 1 by 4n times 4n squared minus 1. And I can expand this term here by using that a squared minus b squared identity. So I have the sum over the positive integers n of 1 by 4n times 4n minus 1 times 4n plus 1. And all we need now is a partial fraction decomposition. So we can expand this as a divided by 4 times n plus b divided by 4n minus 1 plus c divided by 4n plus 1. And this implies that we can write 1 equal to a times 4n minus 1 times 4n plus 1 plus b times 4n times 4n plus 1 plus c times 4n times 4n minus 1. And starting off by allowing n to be 0, well, that means you have 1 equal to a times negative 1 times positive 1 plus 0, which implies that a equals negative 1. Okay, cool. And next up, we can let n equal to 1 by 4, which implies that 1 equals a times 0, right? Yeah. So you have a 0 plus b times 1 times 2 plus 0, which implies that b equals 1/2. And finally, we can let n equal to negative 1 by 4, which means we have 1 equal to 0 plus c times negative 1 times negative 2, which implies that c equals 1/2 as well. And now all we have to do is plug in the values of a, b, and c. So a is negative 1, b is 1/2, and so is c. Okay, cool. And now we can return to our summation problem. So that means s equals the sum over the positive integers n of negative 1 by 4n plus 1 by 2 4n plus 1 plus 1 by 2 4n minus 1. Okay, cool. And let's just factor out a 1 by 2 from the sum. So you'll have 1/2 the sum over n of negative 1 by 2n plus 1 by 4n plus 1 plus 1 by 4n minus 1. And the whole trick here is to expand this term as negative 1 by 4n minus 1 by 4n. And that's exactly what we're going to do. So we're going to write this out as negative 1 by 4n minus 1 by 4 times n. Okay, nice. And now for some rearrangement to give you a better clue into exactly what I'm going to do next. So I have 1/2 the sum over n of 1 by 4n minus 1 minus 1 by 4n plus 1 by 4n plus 1. And I have this term of negative 1 by 4n again. We're now about to invoke the fundamental theorem of flammable maths, which states that if you have an apple and you take it away, then you have no apple, which translates roughly to adding a 0. So what special form of 0 do we need for the evaluation of this infinite series? Well, notice that we have 4n minus 1, 4n, as well as 4n plus 1. So why not go for negative 1 by 4n plus 2 plus 1 by 4n plus 2. So this implies that s can be written as 1/2 the sum over n of 1 by 4n minus 1 minus 1 by 4n plus 1 by 4n plus 1 minus 1 by 4n plus 2. And I'm going to take the other half of the 0 and attach it with this term. as part of another sum using the linearity of the summation operator. So we have plus this other sum, 1/2 this other sum over n of 1 by 4n plus 2 minus 1 by 4n. And I'm just going to invert this. I'm going to write this as 1 by 4n minus 1 by 4n plus 2, and that will introduce an extra negative sign. So I'm going to call this sum here S sub 1 and this one S sub 2. And both of these sums are telescoping series, right? So for S sub 1, I'm just going to expand out the terms, starting with n equals 1. You're going to have a 1 by 3 term, then a 1 by 4 term, plus 1 by 5 minus 1 by 6, plus 1 by 7, and so on and so forth. You get the idea, right? And this is an awfully familiar infinite series, isn't it? Let me just give myself some more space. If I add to it a 1 and negative 1/2 term, and subtract the same, of course, so I have minus 1 minus 1/2 at the tail end, then this here is in fact the series representation of log 2. So this implies that S sub 1 equals log 2 minus 1 minus 1/2 is just 1/2. So you have log 2 minus 1/2 as the first sum. And for the second sum, again, we can factor out a 1/2. So this implies that S sub 2 equals 1/2 the sum over n of 1 by 2n minus 1 by 2n plus 1. And again, we can expand it to evaluate it because it looks like a telescoping series. So we have 1/2 of plugging in n equals 1 gives us 1 by 2 minus 1 by 3. Plus for n equals 2, we have 1 by 4 minus 1 by 5, and so on and so forth. Again, this looks awfully familiar, doesn't it? And if I just introduce a negative sign here, so I can write this as negative 1/2 times negative 1/2 plus 1 by 3 minus 1 by 4 plus 1 by 5, and so on and so forth. Add a 1 here and subtract a 1 from the tail end again. So again, what I have is log 2. So I have negative 1/2 times log 2 minus that 1 at the end. And this here is just this here is just 1/2 minus log 2 by 2. So that's your second sum. And now it's just time to piece everything together. So the infinite series S, and that's not my usual color palette. Yeah, I was looking for a better green. So our series S evaluates to 1/2 of S sub 1. Yeah, there was 1/2 of S sub 1 minus 1/2 of S sub 2. So you have 1/2 of S sub 1 minus 1/2 of S sub 2. S sub 2 is written out over here. That is 1/2 minus log 2 by 2, and S sub 1 evaluated out to this log 2 minus 1/2 term. So you have 1/2 times log 2 minus 1/2, and now it's just time to simplify everything. Log 2 by 2 minus 1 by 4 minus 1 by 4 minus log 2 plus log 2 by 4. So add 1/2 to 1/4, you get 3/4. So that means you have 3/4 of log 2 minus 1/2. And that is what our infinite series converges to. So that was a pretty neat infinite series expansion. And I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.